Eva received her BSc in chemistry and physics in the year 2000 and master's degree in the year 2002 from the University of Calgary, Canada, and then was awarded a PhD fellowship from the Max Planck Research School for Advanced Materials in Stuttgart, Germany. And her postdoctoral research was performed at the Cornell University with Roald Hoffmann in collaboration with Neil Ashcroft. And in the year 2009, Eva became an assistant professor at SUNY Buffalo. And then she was promoted to full professor in 2016. Eva got the Alfred Sloan Fellowship in 2013, the Minerals, Metals and Materials Society Young Leader Award in 2014, University of Buffalo Exceptional Scholar Young Investigator Award in the same year, Quantum Systems in Chemistry and Physics Promising Young Scientist Award again in 2014, and APT Teaching Award in 2016. And also another Chancellor Award for Excellence in Scholarship in 2021, and was named Fellow of American Physical Society in 2021. She's an editorial board member of Physical Review Materials and vice chair for the APS Division of Computational Physics. Eva's research is geared towards studying the electronic structure, properties, and reactivity of a wide variety of materials using first principle calculations. She's interested in high pressure science, superhard superconducting, quantum and planetary materials, catalysis, as well as solvated electrons and electrides. Her group develops algorithms for the a priori prediction of the structures of crystals, interfaces them with machine learning models, and applies them in materials discovery. Eva has been interviewed by Scientific American, NPR's Science Friday, CBS Quirks and Quarks, and other venues on breakthroughs in materials discovery. Eva, the screen is yours.
Yes, so thank you very much for the kind invitation. Can everybody hear me and see my screen?
Yeah.
Yeah, okay, great, thank you. And for the very nice introduction. And it's really a pleasure to be talking after Julia, especially since she has explained a lot of the basic concepts for me and made my job easier. So on this title page, I'm showing two review articles that we've written about on high-drive superconductors under pressure, if anybody is interested in learning more. So to go back, we're going to be in our talk focusing about high-drive materials, though at the end I will mention something about boron and carbon-based materials if I have time. But first I'd like to talk about metallic hydrogen, which was predicted already in 1926 by Bernal and then written about in 1935 in this article by Wigner and Huntington, suggesting that if you put metallic hydrogen under pressure, that it would become a metallic system. And there are two reasons how one can envision hydrogen to become metallic. So first, one could start out with molecular hydrogen, which has a large gap between the bonding and the anti-bonding states of about 13 electron volts. So if you put hydrogen into a solid, it forms bands. And if you squeeze the hydrogen together, then the then you get greater overlap. And because of the overlap increasing, the bands are going to broaden. And at some pressure, you should get an overlap of the conduction and the valence bands, and this would result in what would be known as a molecular metallic hydrogen phase, and this was what could happen under pressure. Another example of metallic hydrogen could be atomic metallic hydrogen, and this is exemplified by the one-dimensional chain that Julia was studying, where if you have an equal distance between all of the hydrogen atoms in this chain, you end up getting a band structure that is the epitome of kind of a one-dimensional metal. And of course, we don't see this at 1 atmosphere because you get dimerization, the formation of H2, and because of that, the opening of a gap, as in the molecular hydrogen. So pressure is going to be able to enhance metallization, either by this band broadening or potentially by stabilizing this type of atomic metallic hydrogen state. And in the 1960s, Neil Ashcroft, pictured here, was the first to propose that if you were able to make metallic hydrogen, then it could potentially be a high temperature superconductor, conventional superconductor, and Julia already talked about that. It would have a large electron phonon coupling because there would be no screening. There are no core electrons to screen the electron phonon interaction, and because of the covalent bonding would lead to this large electron phonon coupling contribution. Moreover, the hydrogen is the lightest material. It has a light mass, and if we look at this formula that gives us the BCS estimate of TC, we have here the omega, which is the average phonon frequency. So if you have light elements, it's going to enhance the TC. And here in this exponential, we have something that is related to the density of states at the Fermi level. So you want something that is a really good metal, has a high density of states at the Fermi level, and also has a large electron phonon coupling. And here I present a more modern version that can be used to estimate TC. This is known as the modified Macmillan-Allen-Dynes equation, and it works relatively well for systems where you don't have a very high electron phonon coupling. But again, some of the keys is you want this large logarithmic average frequency. So light element systems are going to have higher TCs, and this large electron phonon coupling constant, which would be present in hydrogen because of the covalent bonding and the lack of the screening. So afterwards, Neil Ashcroft proposed, because you can't metallize hydrogen at low pressures, and metallization at high pressures, though it has been achieved, it is undoubtedly occurred at high temperatures, but at low temperatures, there are a number of experimental challenges. For example, the hydrogen reacts with the diamonds in the diamond anvil cells, so you have to coat it, and there are a number of challenges associated with making sure that, characterizing whether or not you have achieved a metallic state. So Ashcroft proposed that potentially we could lower the pressure associated with metallization by doping with another element. And the first system that he looked at was silane, and he said that potentially adding silicon to hydrogen could induce chemical precompression. So what that means is that the silicon addition would actually increase the density of hydrogen as it would be without silicon compared to what you would have without silicon, and the resulting system would have all of the desired properties for high temperature superconductivity. And the initial focus, first of all, theoretically, there was a lot of theoretical calculations done, was on systems like silane and germane, because silane is isoelectronic with MgB2, and we know that MgB2 has a high TC of 39 Kelvin as a conventional superconductor at 1 atmosphere. And there was also experimental attempts to metallize SiH4, though these experiments, the interpretation of these experiments has been questioned as to whether it is really SiH4 or some other compound that is giving rise to the superconductivity. Nonetheless, this really brought about a large number of people doing computations trying to predict the crystal structures of high pressure hydrides mixed with some other element, and then also followed by other experiments. And so here I show that, about a decade later, pretty much all of the binary hydrides have been studied computationally. And this is the periodic table of superconductivity in binary hydrides that shows a number of the trends that Julia already emphasized. And if you have the addition of an electropositive element, such as an alkaline earth or a rare earth metal with hydrogen, you get the highest predicted TCs, of course, under pressure only. And there are some other regions where you might have a high TC value, for example, SH3. And this table is a little bit incomplete. This contains both theoretical predictions and some experiments when they were available. And this was made a couple of years ago. And in the last few years, a number of theory groups have studied, for example, neptunium or plutonium hydrides under pressure. So I would like to point out that this H3S compound was actually made at about the same time that it was theoretically predicted, and the TC matched really well the experimental TC with the measured TC, and that was done in about 2015, it looks like here. And then 1 year later, this lanthanum H10 compound was made by two different groups, Arametz and Henley, and its TC was measured. And again, this was actually a theoretically led, so the theory came first in this case, predicting that lanthanum H10 would be a very high temperature superconductor. And other compounds, such as calcium H6, were predicted and then eventually made, though the synthesis ended up taking later. And then MH9, Julia talked a lot about YH9, so that's another well-known prototype structure for a number of these high-pressure compounds. So what we note, though, is that the electropositive elements, when they do have very high TCs, assume one of these types of structures, whereas when you have a p group element, the chemical bonding is quite different. Here we see that the sulfur forms a multicentered bond with hydrogen, where the hydrogen kind of bridges these two sulfur atoms. That would obviously not happen without pressure. And in these types of systems, we see hydrogen forms bonds with other hydrogen atoms, and there is only kind of an ionic interaction with the electropositive element. First, let's look at the electropositive dopants, why some systems have high TC, why others do not, and think about the mechanism of metallization. Remember, we want a high density of states at the Fermi level. That's one of the criteria for a high TC, and also a large electron-phonon coupling. So if we have only H2 molecules in the system, in the stable systems under pressure, one example that was predicted is this LiH6. The reason why you get metallization is the electropositive element is going to be donating electrons into the H2 antibonding bands, and so these types of systems are metallic already at 1 atmosphere, though they are not going to be stable, and superconductivity can occur with usually relatively decent TCs, but nothing approaching room temperature superconductivity. Another motif, chemical motif, that we have seen in a number of the high pressure hydrides is where you have H- units that are formed, such as in this sodium H9 compound. And in this case, the sodium donates electrons to this H-, and one would have an insulator at 1 atmosphere. If you put pressure on the system, you end up getting this band broadening and eventual overlap. However, the density of states at the Fermi level is not high in these systems, and it is usually, the metallization pressure is usually underestimated with standard PBE gradient functional. So these types of systems are usually not very good high temperature superconductors because of this low density of states at the Fermi level. Another hydrogen motif that one can find in these high TC hydrides would be the formation of H3 minus type units. And here I show the kind of cartoon molecular orbital diagram of H3 minus. Again, we have this large gap between the bonding or the antibonding and the non-bonding orbital. And under pressure, we get an overlap of these bands formed from these orbitals. And again, the TC is not going to be high because the density of states at the Fermi level is not high. However, what we see as the best candidates for metallization are ones that would be similar to this one-dimensional hydrogen chain that I talked about at the beginning, which is going to be a good metal even without donation from any sort of other element. So here I show a predicted SRH6 phase that has exactly such a one-dimensional hydrogen chain. It's a good metal, and it has a high TC, but you can actually increase the TC if you increase the dimensionality of the extended hydrogen network. So if you have a system with a 2D plane or with a 3D cage, like in these clathrate materials, the number of bonds that can undergo electron-phonon coupling is going to increase, and that increases the TC. So this goes into the review article that we have written, where we have surveyed a number of the different cases with high TCs and looked at the trends that are found in their TCs. Again, if you have systems with mixed molecular and atomic hydrogen, they are similar usually to the sodium H9 case that I talked about earlier, and TCs at various pressures, these are predicted TCs, can go typically up to about 100 Kelvin, though there are some exceptions, such as in the scandium H7. And the reason for this exception is because the valence of scandium is actually going to be a 3+, and there is some electron charge donated to these H2 units whose are going to lead to the metallicity. Then there are these other unique hydrogenic motifs, either one, two, or two-dimensional hydrogen chains or sheets, or in some cases, these pentagraphene-like units. And they have intermediate type TCs going up to about 150 or so Kelvin. Again, these are mostly predictions. And then finally on to these clathrate superhydrides, as they are called. They have these types of three-dimensional lattices where you have really hydrogen bonds forming, really weak hydrogen bonds formed in the lattice, and then the metal atoms stuck in the center and clathlated within these cages. And they are predicted to have the highest TCs, of course, only at very high pressures, but some TCs actually reaching that of room temperature. And as mentioned by Julia, though we can reach very high TCs in some of these systems, it's only at high pressures, so we need to go to ternary or potentially quaternary hydrides because potentially adding in these extra elements can give rise either to higher TCs, as has been predicted in this hot superconductivity for the lithium-2 magnesium H16, so TCs above 400 Kelvin at 250 GPa, or to a lowering of the pressure at which superconductivity can occur. Again, this is a prediction which has actually been recently verified by Yaming Ba's group in the synthesis of lanthanum and beryllium H8 with this same structure. And this is actually derived structurally from this MH10 cage, as I'll talk about later. And then finally, as I mentioned, the different case of the superconducting hydrides are those where you have covalent bonds formed between the hydrogen and typically some sort of a p-block element, such as in the H3s system, or as in this phosphorus hydride system that was only published on arXiv by the Aeronets group, and then studied theoretically the most likely phase that we believe could have this high TC is shown here, pH2, where you have a covalent bond between phosphorus and the hydrogen atom. Okay, so obviously these are very strange systems that we would not be able to, as chemists, predict using our knowledge of chemistry at 1 atmosphere, and also these types of systems are not found within databases, so engineers would not be able to predict them. So how do we go about predicting them? There are a number of approaches that have been employed within the last decade based on crystal structure prediction methods. Some of them are evolutionary algorithms, which is the approach my group uses, and I'll talk a little bit more about that. You can use random searching as in AIRS. Calypso is the particle swarm optimization techniques, and USPEX is another evolutionary algorithm that is used. So all of these techniques can be used. I'll discuss one of them a little bit more later. What happens then is the user inputs either some sort of a stoichiometry or a list of potential stoichiometries into the system. Then the crystal structure method finds the most stable structure for the particular composition. And then one scans the different types of lists of compositions and plots. Here I show the enthalpy of formation of the hydride material as a function of the H2 mole fraction. So this would be 100% hydrogen. This would be 100% the other metal, assume it's calcium. And then one looks to see what structures define the so-called convex hull. And all of the structures on this convex hull are considered to be thermodynamically stable. Systems above the convex hull might be metastable, provided that their phonon modes are all real, and they could potentially be synthesizable. Then there are another number of questions in this. For example, these are light element systems. If we consider 0-point energy, the convex hulls might change, as shown schematically right here. And also, if we consider finite temperature effects, that might have an impact on the convex hulls, and these are typically not considered due to the immense amount of computational expense that would be needed. So then we need to decide, what do we study? Thermally stable compounds, kinetically stable compounds, reaction barriers. Another idea that one can use, instead of doing this whole really expensive process, is if you find a particular prototype structure that seems to have a very high TC, then one can do high throughput screening by just replacing elements in that prototype structure. And that may be used to potentially find metastable species with a desired type. So the next thing that is typically done in this screening is as I mentioned, we want to have a system with a high density of states at the Fermi level. That would be a good superconductor. So we need to define some descriptors. One of them could be the method that Julia discussed in the networking value. And then there are also practicalities. We don't want things with low symmetry or huge unit cells. If we want to actually compute from density functional theory what the superconducting critical temperature would be. Otherwise, other models, such as the model that Julia described, might be useful when we cannot, for practical reasons, compute the TC from first principles. And then if we do want to compute the TC from first principles, I note that there are a lot of different approximations that can be used. And so if you see different values in the literature, it depends about the approximation and also about how careful the authors have been in the computational settings. Okay, so now let's discuss the crystal structure prediction. So what my group uses is this so-called Xtlopt code. And how it works is you first generate a large number of structures, either randomly or pseudo-randomly. I'll talk a bit more about that later. Then these structures are sent out to your favorite program. In our case, it's VASP. They are optimized to the nearest local stationary point. And then our code Xtlopt goes out to see which structures, what the enthalpies of these structures are. And a fitness is assigned to these structures based upon their enthalpies. So the most stable structures are going to have the highest fitness. Then the structures are going to be chosen for procreation, so the parent structures based upon their fitness. And then there are a variety of genetic operations that are applied to the structures. So one operation could be taking two different crystal structures and cutting them at some kind of a random position and then splicing them together. So this imitates what is known as a crossover or a breeding type of operation where you take two parents that make one structure. Otherwise, one could have just permutations of single structures. So here we take one structure and strain the unit cell, or we take a structure with two different atom types and swap the atoms, or you can put a ripple through the unit cell. So new children's structures are made via application of one or a combination of these different operations. Then these are sent out for local optimization again. And then the method looks to see whether or not you have so-called converged. The idea of convergence differs on each user that applies this method. If you think you have found the ground state or the most stable state, the structure with the highest fitness, then you stop the algorithm. If you haven't, then the algorithm continues. So this program, Xtlopt, has been interfaced with various codes. It's available under open source licenses, and it's cross-platform, and it can be run either using a command line interface or a visual interface. And what I would like to note, as Julia mentioned, is that we are going to be trying to find potentially some of these metastable structures that have high TCs by using the TC prediction that she has put forward along with Xtlopt in a multi-objective search. So what I mean by that is that this fitness that is assigned is not only based upon the enthalpy or energy of the structures, but it's based upon some sort of a linear combination of enthalpy plus the predicted TC. And in this way, we can hopefully target metastable phases or high temperature phases that could be made in experiment. Okay, so this is a paper about Xtlopt. Some of the recent advances the advances that we've made in the last decade or so is that in the first generation, if you use randomly made symmetric structures, we find that you can converge to the global minimum much more quickly than if the structures are just completely random. We've also introduced a duplicate matching scheme. So that is a scheme that figures out if two structures in the so-called breeding pool are actually duplicates of one another. They need to be removed from the breeding pool, because if they aren't, then your algorithm does not sample the whole potentially energy landscape. And as I've mentioned, we have this multi-objective search that will be soon published. Okay, so that's my background. So hopefully now I can show you a few of the results that we have in the last years, and I probably won't get through all of them. As I mentioned previously, the sulfur hydride systems is one of the most iconic ones for the high temperature superconductivity. So we were thinking about what would happen if we dope sulfur hydride with another element that is quite similar. And the element that we chose is phosphorus. We also looked at carbon, but I won't discuss that here. I would like to focus on phosphorus. So if you do a crystal structure search, you can generate these convex hull type plots. In this case, this is for a 3-component system. And what I'm showing are the black dots are those that lie on the convex hull. And the colored dots are ones that are above the convex hull, meaning they are metastable, and this is the hull distance. And I note that if you look at the materials project and the data found within the materials project, the 90th percentile of DFT stability is about 70 MeV per atom. So that does not necessarily guarantee that if a structure is 70 MeV per atom above the convex hull, it can be made. But what it does say is that is not a bad criterion for deciding which structures could potentially be synthesized in experiments. So we focused on studying a number of these systems that were within this kind of potential synthesizability zone. And there were a number of different families found. Sulfur here is yellow, phosphorus is orange. Some of them have these 2D honeycomb hexagonal networks. Other ones have 2D kinds of sheets, 1D chains, and then also cage-like systems that could be related to the parent SH3 compound, except with sulfur substituting one of the phosphorus atoms. And we chose those that had a high density of states at the Fermi level and also relatively high symmetry to perform the electron-proton coupling calculations on them. And here are some trends that we observed. If you note that just systems with pure sulfur phosphorus have a relatively low TC, adding hydrogen to these systems raises TC by about an order of magnitude. But the highest TCs that we found were for these doped sulfur high SH3 type systems. And here I plot the density of states at the Fermi level for H3S and also for this 12.5% doped phosphorus system. I note that it is actually a tiny bit higher than for H3S. However, obviously the weight of phosphorus is far higher than the weight of sulfur. And therefore the TC of this doped phase is predicted to be approximately the same as that of H3S. So I give two numbers here. One was estimated with the Allen-Dines formula, and the other one is estimated by the solution of the Eliashberg equations, which is more accurate for systems with a large electron-photon coupling. Another possibility would be to combine the calcium H6 with SH3. So we wanted to study what would happen in that situation. And actually, it should not be surprising that many of the systems that we predicted to be stable could be thought of as being basically calcium sulfide, Ca2 plus, S2 minus, with H2 molecules stuck within it. And these systems are not good metals or not metallic at all at the pressures that we looked at. So they are not good candidates for superconductivity. There was only one potentially good candidate for superconductivity found at about 300 GPa. It was predicted to lie on the convex hull, including the 0-point energy. And I show it right here. It once again has these multi-centered hydrogen sulfur bonds, and it can be thought of as kind of a two-dimensional version of H3S with these honeycomb HS lattices that are separated by calcium H2 type two-dimensional sheets. And here I show the density of states plot. We see that we are really near to this peak in the Fermi level, and this is one of the reasons why this system could have a potentially quite high TC. And if we decrease the pressure, what we'd find is that we actually increase the value of the density of states at the Fermi level. And because of that, we increase the TC, which is calculated to potentially reach as high as about 100 Kelvin at the kind of onset of dynamic instability, near the onset of dynamic instability. We have then used this structure as kind of a prototype and performed a high throughput search where we replaced the calcium here by other alkaline earth metals and the sulfur by tellurium or selenium, or keeping it with sulfur, and looked at the range of the dynamic stability. If we have an X, that means that the system is not going to be dynamically stable, and estimated TC for the dynamically stable phases. The highest T system we found was strontium tellurium H3, predicted to have a TC of about 90 Kelvin with Allen-Dines, or 120 Kelvins with Eliashberg formalism. And I would also like to mention that we looked at the kinetic stability. So we performed molecular dynamics simulations showing that this structure will not fall apart. So if it could be made at very high pressures, it could potentially be quenched to 40 GPa without falling apart. Though I would like to point out that it is never really the most stable phase. Performing full crystal structure prediction calculations for SRTE-H3 yields a number of other quite interesting phases shown right here. I will mention very quickly, as we know, there was this work performed last year on the lutetium nitrogen hydrogen, suggesting that it could potentially be a room temperature superconductor. And we tried to predict computationally what this structure might be by doing just a normal crystal structure prediction search, as I mentioned earlier, or by using constraints. There were constraints that were proposed in this manuscript based upon the positions of the lutetium atoms. So we knew what the unit cell should be for the heavy element systems, so we could implement that as a constraint in the crystal structure search. And we also used prototype modification and so on, and compared the similarity of the experimental and theoretical X-ray diffraction patterns. And we did not find any high TC structures. The highest TC structure that we found is shown here. However, it is extremely high above the convex hull, and it had a TC of only about 17 Kelvin, depending upon exactly how you calculated it. Though there have been other recent predictions of possible structures with larger unit cells that have interesting electronic structures that is considered that could potentially have a high TC. However, their unit cells are so large that it is not possible to calculate TC except by using kind of descriptors similar to what Julia described. Okay, I don't think I want to talk too much about this because it's a whole different topic. Oh, well, actually, okay, I will mention it. So one of the things that we wanted to look at is the chemical pressure. So what the chemical pressure is, this is actually a method that was introduced by Danny Fredrickson, is talks about if you have an atom with a particular ionic radius, or just radius in general, what kind of local pressures are induced by that element within the crystalline lattice. And how you calculate chemical pressure is by doing an expansion, a slight expansion or a slight contraction in your DFT calculation, and then calculating the pressure defined as this dE over dV, and doing so on each voxel within the calculation. And then the chemical pressure maps can then be mapped onto these types of spherical harmonics. And what this type of method shows you is if you have this kind of a positive chemical pressure, it tells you that the lattice would like to expand along that direction. And if you have a negative chemical pressure, these black lobes, then it would like to contract around that position. So we wanted to take a look at why in some of the high pressure hydrides you get the stabilization of these three-dimensional lattices with high TCs, and in other hydrides, so this is calcium H6 and strontium H6, on the other hand, you get what is known as a Peierls distortion. So these three-dimensional cages distort into these types of one-dimensional chains, and because of that, TC is lower. And obviously, this is going to be a size effect, which is what we found. The strontium H6 is somewhat going to be too large for this type of a cage, and this type of a distortion is preferred. But going on to the ternary hydrides, how could we design these types of ternary hydrides using the chemical pressure map idea? So if we start from lanthanum H10, this is another way to visualize it, not as calathrate cages, but as these kinds of cubes that are going to be linked by tetrahedra. So you have vertex sharing H4 tetrahedra and H8 cubes. And if we see the chemical pressure map, we see these types of lobes pointing from the hydrogen to the lanthanum atoms is the most standing out technique. If we then remove the hydrogens inside these H4 tetrahedra, we get really large negative pressures directed inside them. And so one of the ways to relieve these negative pressures is to expand the cubes by putting boron or beryllium or other atoms within the cubes, and then you get this kind of a minimization of the excess chemical pressure. And this lanthanum BH8 or beryllium H8 or other types of compounds that have been predicted in this family, this is one of the reasons why they are stable, and they are stable to lower pressures than some of these really high pressure lanthanum H10 systems. If you look at yttrium H10, on the other hand, yttrium is going to be smaller than lanthanum, and so it has a different chemical pressure map. Again, if we remove these hydrogen atoms within the tetrahedra, we have a different type of a chemical pressure system. And so if we stuff these types of cubes with another element, we do not get dynamic stability. But dynamic stability can be achieved if we put a carbon or a boron atom, for example, within the tetrahedra, giving rise to the formation of these kinds of methane or BH4 type units. And so we predicted using this kind of a methodology that yttrium C2H8 could be stable at 50 GPa with a TC of about 60 Kelvin. Using this again as a prototype, this type of a system, we studied a number of different high pressure hydrides where the central atom here is either replaced by a boron or by a carbon atom, and did a high throughput type search, varied across the different pressures. And what we ended up finding is that you have a number of different TCs, with the highest TCs predicted for the potassium and rubidium and cesium type systems. What I do note, on the other hand, though, is that though these TCs are very high at low pressures, if you take a look at the molecular dynamics simulation, what we find is that at these lowest pressures, so 12 GPa or whatnot, the dynamics predicts these structures to be actually unstable. So you're going to overcome barriers, and the system will form these kind of unwanted units and actually an insulator, and it's not going to be good for superconductivity. So our molecular dynamics simulations suggest that you need at least 50 GPa of pressure to stabilize these systems, and therefore looking just at the dynamic stability is not sufficient to predict when different structures with various TCs, high TCs, might be stable. I would like to very quickly mention that these types of ideas can actually be used to predict other superconductors based upon light elements that could potentially be stable at 1 atmosphere. So returning to these very familiar clathrate-like cages with hydrogen, we know that if we take away the pressure, they're going to decompose at 1 atmosphere. But if you replace the hydrogen atoms with potentially carbon and boron atoms that can form strong bonds with one another, you could get stabilization. And this was actually first shown by Tim Strobel and Li Zhu in this predicted strontium B3C3 system that was synthesized under pressure and quenched to 1 atmosphere. It didn't survive for too long. It was very air sensitive, though this was a design principle that was shown could be used to make other systems. And there were TC predictions that it could be as high as 43 Kelvin under pressure. And at 1 atmosphere, though TC has been measured under pressure, but it is lower than this. So we wanted to take a look at what would happen if you took this design principle and instead used different elements, for example, different alkaline earth, alkaline metal atoms, and potentially some of the main group type atoms. So we performed, again, a high throughput type search. The X's denote compounds that are not dynamically stable at 1 atmosphere. And then the other blocks are showing you the predicted TCs for other binary boron-carbide type systems. And what we note that the B6C6, if you had a trivalent, two trivalent elements within it, this would be isoelectronic to carbon, to diamond. And so the Fermi level would fall right here, and you get an insulator, which is not going to be superconducting. And this is the reason why the yttrium and lanthanum versions of this compound are predicted to be insulating with 0 TC. If, on the other hand, you have a different valence, so 2+ or 1+ or some kind of combination of them, you are going to be varying the position of the Fermi level. And if you can engineer your system so that you hit one of these high peaks in the density of states, then you could potentially get a very high TC. And one can do that. If you take a look at the trends in the TC, we see various trends. Systems that have that hit this peak, that are an average valence of 1.5+ have the highest TC. With this potassium lead compound, this is at 1 atmosphere, having the highest TC of 88 Kelvin. Systems that have an average valence of 2+ are close to this peak. For example, this phase with a TC of about 50 Kelvin. And then systems with lower average valences would have a smaller density of states at the Fermi level. And this is the reason why their TCs are predicted to be lower. Okay, so these are some of the trends that we've noticed, and we've also taken a look at the Vickers hardnesses. And as I noted before, it's important to think about different ways that stability is defined. Though this potassium lead compound is dynamically stable at 1 atmosphere and also stable according to the molecular dynamics simulation, if you take a look at just the enthalpy of formation, it doesn't suggest that it's going to be stable. But if you then consider other factors, for example, the finite temperature effects on the Gibbs tree energy, and also potentially configurational entropy. So what I mean by configurational entropy is if we assume that there is no site preference for the potassium and for the lead in a really large system where you could have disorder on the metal sites, then this would introduce configurational entropy that could be used to stabilize the system. And taking these types of situations into account suggests that this type of a solid could be made under pressure and potentially quenched to atmospheric. So the last thing that I would like to mention very quickly is that one can also use these methods, multi-objective search, to propose super hard materials. So using not only the enthalpy, but also the estimated Vickers hardness to find stable phases. And we have done this in this manuscript right here, focusing on phases that have a low enthalpy and a high Vickers hardness. And actually, then after screening some of them, we found that a couple of phases had a high density of states at the Fermi level. And this is one shown right here. And what it can be thought of as being these types of polyacetylene type chains that are held together by these sp3 carbon network, and that is imparting a pressure on this system. So this is the reason why we call it diamond anvil cell carbon, because of this artificial pressure. These would prefer to be around 4 angstroms apart from one another in the solid state, but because of these black carbon atoms, they are actually constrained to be about 2.57 angstroms close to one another. And we can estimate what the pressure imparted by this lattice is. And one can do molecular dynamics trajectories to study the kinetic stability and look at phonon stability and so on. And we do find that these could potentially be made at mild pressures. But what is interesting is to note the electronic structure. So if you take these carbon chains and pull them apart, what you are going to see is that this is a nice insulator. But if you squeeze them together, what you end up doing is at the gamma point, you actually get a large overlap of these p orbitals of the neighboring chains. And this is an anti-bonding type situation. So you end up raising the energy of these two bands. At the Z point, because you have this bonding type situation, you end up lowering the energy of these two bands. And because of that, this kind of pressure induces metallization. And if you have this metallic carbon type system, you could potentially have superconductivity. And we studied that. The superconducting critical temperature of this so-called DAC carbon is quite low. It's only 1.6 Kelvin, but it's quite similar to that of twisted bilayer graphene, which is one of the rages in material science nowadays. And we can show that the superconductivity is due to these two flat bands. Okay, and we predicted the synthesis route. So that's all I wanted to say. Here are some conclusions. My collaborators on the work that I've shown are Tim Stropel, Li Zhu, Davide Proserpio, and Stefano Cordarolo, and I'm really excited to collaborate with Julia on the next version of this as we implement the multi-objective search, looking for metastable systems with hydride-based systems with high TCs. And these are my group members. The ones that have contributed the most to this work are Katie, Busheng, Nisha, Zhao Yu, Francesco, Samad, and Stefano and Morgan, and also to the funding agencies. And I'd like to ask you for any questions.
Thank you, Eva. We already have somebody writing, but before, maybe I will ask. So you showed us beautiful structures where the hydrogen atom was forming some kind of a bridge between two other atoms, like sulfur or phosphorus. It's a very naive question, but this reminds me the ice structure and water and oxygen never appeared in your structures. Why?
Okay, yeah, so it is. It's very similar to the multi-centered bond formed in H2O under pressure. You get this hydrogen that is bonded to two sulfurs as opposed to two oxygens. So the water type structures actually don't become metallic until very high pressures. And for that reason, they can't be superconducting. And I'm sure there is some explanation with respect to the, electronegativity or whatnot that can be used, but they don't become superconducting because the metallization pressure is just so high.
In your first example of results, you were showing predicted prediction of superconductivity under pressure 40-50 gigapascals, and that's already really quite easily available when one is using membrane ducts and so Has anybody tried to confirm this kind of your prediction with experimental studies of such systems?
Yes, so actually, there was a paper on lanthanum beryllium H8. That is not my prediction. I believe a couple of different groups, including Lilia Boeri, predicted that structure or very similar structures. And there was a paper in PRL by Yaming Ma, and they were able to synthesize that structure. I don't remember the details. Maybe it was 80 GPa, but it was very similar to the actual computational prediction.
Thank you. Oh, there are first questions. Hans Birgi, what are the H to D isotope effects in these hydrogen-rich superconductors, partial or full H to D replacement, lowering TC?
Yes, that's exactly one of the things that is done in some of the experiments is if you can replace with deuterium, then there's, you can compare the TC of the two systems, and that will help confirm whether or not this is conventional superconductor. So I'm pretty sure this has been done by Mikhail Aramet's group for some of the systems. Experimentally, you can do it as well. Theoretically, of course, you can do it as well. And because the deuterium is heavier, then the TC should decrease.
Okay, thank you. And Marcin Mazjasz, how do you estimate, calculate hardness? I mean, these super hard materials.
Yeah, that's a great question. So there is no good way to really either measure or calculate hardness. Even in the measurements, it depends on what type of probe you use. Do you do nano indentation or micro indentation, and what kind of load you use, and so on. But what we have done is we looked at, there are a couple of different formulas that have been proposed, analytic formulas that are based upon the bulk and shear moduli. And we used the tetra model, which is something called 0.151 times the shear moduli. And that shear moduli, what we have done is we actually used a machine learning model that was trained on the systems within the AFlow database to get the moduli. So getting those moduli takes a fraction of a second because it's done with a machine learning model, and then we have an analytic formula to estimate hardness. But yeah, that's one way you can do it, and of course it's has errors as do the experimental measurements.
Thank you.
Yes, you can. You can also do the elastic constant calculations, but those are not quite as quick as the machine learning model.
Yeah, so the maximum number of different chemical elements in your structures was 4? Was
yeah, so when you look at the pure crystal structure prediction techniques, most of them have been applied to the 2-element hydrides, right? That has been done very well. When you go to systems with 3 elements, the number of possible structures that have been made could be made. The number of stoichiometries just starts to explode, and then the crystal structure prediction searches that were done in the past were not necessarily as thorough, just because you can't consider all of the stoichiometries, and then also finding the most stable stoichiometry for structure for that particular stoichiometry just needs a lot more DFT calculations. And that's one of the reasons why people have started using prototype structures to study 3 or 4 element systems. But I do say that there are some new things coming up. Instead of using DFT calculations. One can use machine learning models to try to scan the stoichiometry space and figure out what types of stoichiometries you should use DFT to study. So that is being done also by a number of groups as we introduce the machine learning models for the enthalpy evaluations. That's going to become much more common. So yeah, we've looked at four component systems, but that was not using structure search. That was based on prototype structures. And structure search has only been done usually up to 3 component structures, but on a much smaller subset of stoichiometries than we would ideally like to include.
Both Julia and yourself, you were showing such beautiful illustrations of average structures. In fact, when you do so-called per distribution function studies, they clearly show that real structures, that these are the average structures, means in practice, in crystal lattice, you have like a distribution of atomic ionic positions around those average ones. Does this matter that in reality you do not have this ideal order in your structures?
Yes, so there's a few things that are going into this idea. So the first thing is if you do you know, some sort of molecular dynamics calculations, just classical, normal molecular dynamics, I mean, classical nuclei, quantum electrons, then what you find is that the hydrogens, because they're light, they end up being mobile at lower temperatures than the heavy elements. So you can get some wiggling or whatnot of the hydrogen lattices. And that will affect your density of states at the Fermi level, and that will affect the superconducting critical temperature. So that's one thing to note. And the other thing to note, though, is that when you take into account the quantum nature of the protons, that's the kind of work that Jan Area would do, that will have another effect. So I'm not sure about the quantum molecular dynamics, but I do know that when they have included the quantum corrections into taking a look at the stability of different structures. So for example, you can, this lanthanum H10, the hydrogen lattice, you can imagine you can perturb it a little bit. And actually in the normal DFT calculations, such perturbed structures are going to be more stable at lower pressures. But if you include these quantum nuclear effects, what ends up happening is that the potential energy landscape changes and the symmetric structure is actually going to be the ground state. But that, yeah, I'm not quite sure how that translates to the dynamics. I haven't thought that far about it. But those are two things that are important.
But definitely, hydrogen should behave in anharmonic manner because they are so light. I mean, it's in all those structures. Do you account for anharmonicity of hydrogens in that studies?
So most of the time we don't, but sometimes we do. And that again is the work done by Jan Area primarily, and now one of my postdocs, Francesco Belli, is looking into such effects. But you only can really do it for 1 or 2 structures. You can't do it for every structure, just because of the computational expense. Though again, I think machine learning models for doing the quantum enharmonic simulations are going to change this. So we will be able to look at more structures in the future. So in the crystal structure prediction, you don't include it. You include it afterwards when you've figured out which structure you want to look at. sometimes if you have the knowledge of how to do it and the computational time.
We have congratulations from Sina Larsen. I do not see. Oh, Mr. Mazdziarz is typing next question, so let's wait for this. Molecular dynamic unharmonicity is naturally included.
Sure. I guess I meant the quantum nuclear effects too. So yeah, those are typically put in as an add-on, and most people, when they do electron phonon coupling calculations and TC estimates, do not include these effects because they're based upon harmonic phonons, though you can include them afterwards.
Yeah, these are very special systems. Probably it's not easy to make them to make hydrogens, hydrides of such.
You mean to synthesize these
Yes.
predicted structures, right?
Yeah, I mean, I don't know how easy it is. People are getting better at it for sure. So there have been, you know, to make the sulfur H3 and lanthanum H10, it took a long time, and nowadays it seems that a number of phases have been made, like the YH6, YH9, various other hydrides. I almost feel like I can't keep track of it anymore. Lanthanum BEH8. So I think there are some know-how that has improved. For example, in what precursors you use. I think the ammonia borane is used as a hydrogen precursor often. So there have been definitely some knowledge advances.
In those hydrides, if we go with a number of hydrogens to infinity, would this give us properties of just pure hydrogen structure?
Yeah, it should. Though if you, I mean, in principle, if you have an electropositive element in a huge hydrogen matrix, it should dope it, right? But yes, in principle, you should go to a pure hydrogen type structure.
But do you go in this direction? I mean, with your predictions. I mean, if
yeah, I mean, we haven't studied really high numbers of hydrogen atoms yet. There have been other groups that have looked at higher hydrogen content, but I think they have also found some other large cloth rate cage type structures, though their hydrogen content was not huge. So,
yeah, would be interesting to have hydrogen in ice. Okay. We do not see anybody else typing questions. So, Eva, thank you very much.
Okay.
Julia, thank you very much. Thank you for this really excellent webinar.
Yeah, and thank you for organization.